All right, in this video, this is a continuation of section 5.1 dealing with approximating areas under curves. And in this video, I'm going to talk about sigma notation. Okay, so that's the first thing we'll talk about, sigma notation. And then also we're going to be using sigma notation to help us find Riemann sums that we talked about in the previous video. All right, so sigma or summation notation is what they call it. If you were working with Riemann sums, that can be cumbersome if you were dealing with large numbers of subintervals. Let's say you did 30 subintervals or 60 subintervals or even 100 subintervals. That can be time consuming if you were using Riemann sums. So here we're going to introduce some notation that will simplify your work. All right, so here we use sigma notation, or they call it summation. That's going to be used to express sums in a compact way. So, for example, the sum of 1 plus 2 plus 3 plus and so on up to 10, we can express that using sigma notation. So here, this is the Greek letter sigma. And it's the Greek capital letter S, meaning the sum. So for this expression, we can write that as the summation from k is equal to 1 to 10 of k. Now let me explain what this means. Your index is going to be k. That takes on all integer values from the lower limit, which is k is equal to 1, to the upper limit, k, which is 10. So this is your lower limit down at the bottom. Your upper limit is on the top. So it'll be k equaling from 1 to 10. The expression that immediately follows that sigma notation, that's called the summand. So that k right there is your summand. That's going to be evaluated for each value of k, and the resulting values are summed. Like for some examples here, let's say the summation from k is equal to 1 to 99 of k. That's going to be this, 1 plus 2 plus 3 all the way up to plus 99. Add all those numbers up, you'll get 4,950. And then in general, the summation from k equaling to 1 to n of k would be 1 plus 2 plus and so on all the way up to that upper limit up here, which is n. Or the summation from k equals 0 to 3 of k squared. Notice it starts at 0 for k. So it'll be 0 squared plus 1 squared plus 2 squared up to plus 3 squared. Square each number, add them together, you'll get 14. And then also from the summation from k is equal to 1 to 4 up 2 times k plus 1. That means this. Each k value we substitute with 1, and then that will give you 3. Then the next one will be 2. 2 times 2 will be 4 plus 1, which will be 5. Then for 3, 2 times 3 will be 6 plus 1 is 7. And then for 4, and we stop at 4, 2 times 4 is 8. 8 plus 1 will give you 9. Add 3, 5, 7, and 9 together, you'll get 24. And then the summation from k is equal to negative 1 to 2 of k squared plus k. So we start with negative 1, and then 0, then 1, and then 2. Simplify each one of these, get the sum, you get 8. Okay? Now, the index in a sum is what we call a dummy variable. It is internal to the sum, so it does not matter what symbol you choose as an index. So like, for example, we could use k as a dummy variable. The summation from k is equal to 1 to 99. Or you could use n for the summation from n is equal to 1 to 99. Or you could use p for the summation from p equals 1 to 99 of p. So these indices or the index represent just a dummy variable. Now we do have two properties of sums that are useful in upcoming work. Okay? So here we got the constant multiple rule and the addition rule. The constant multiple rule is this. If you have the summation from k is equal to 1 to n of some constant c times a sub k, we can pull the constant out in front of the summation notation. So it'll be c times the summation from k is equal to 1 to n of a sub k. And also we can split a sum into two sums. That means if I have the summation of the sum, I can take that and break it up as the sum of the individual summations here. So the summation of from k equal 1 to n of a sub k plus b sub k, I can write that as the summation from k equal 1 to n of a sub k plus the summation from k equals 1 to n of b sub k. Okay. All right, now on the next page, we have formulas for sums and powers of integers. They're also going to be essential here. Okay? Like in this case right here. We'll start with letting n be a positive integer and c be a real number. So here, the summation from k equal 1 to n of some constant c, that's just going to be that constant times this upper limit, which is your n. So it'll be c times n. And then the summation from k equal 1 to n of k is going to be expressed as this. N times the quantity n plus 1 divided by 2. Your n is your upper limit. So it's going to be the upper limit times the sum of your upper limit plus n1 divided by 2. And then for the summation from k equal 1 to n of k squared, it would be this expression. N times n plus 1 times 2n plus 1, all that's divided by 6. And then finally, the summation from k is equal to 1 to n of k to the third, that would be this, n squared times the quantity n plus 1 squared, all divided by 4. Okay? Now, in another video, I'm going to show you how to use these formulas here to do some of the problems that I'm going to talk about. However, you can use a graphing calculator to do this, and you have to have a TI-84 plus calculator to do this because it will give you the summation symbol right off the top. And you can easily just fill in what you need in order to get that summation. I'll show you that later on in this video. Let's look at example 6 first. We're going to express the sums or the following sums using sigma notation. We're going to express the following sums using sigma notation. So in part A, we got 4 plus 5 plus 6 plus 7 plus 8. And in this case here, we do need the summation notation, so we have the summation. And I'm going to use k in this case, so we're going to start from k is equal to 1 to, I'm starting with 1 here in this case. So the summation from k is equal to 1 to, now how many numbers do I have here? Let's count. I have 5 numbers, so that's going to be my upper limit, which is 5. So it'll be the summation from k is equal to 1 to 5. Now, to get the expression here, if I'm starting with 1, from 1, I need to get to 4. So what number added to 1 will give me 4? Has to be 3. So it'll be k plus 3. And it makes sense because if I start with 1, that'll be 1 plus 3 will give me the 4. For 2, 2 plus 3 will be 5. For 3, 3 plus 3 will be 6. For 4, 4 plus 3 will be 7. And finally for the 5, 5 plus 3 will give me the 8. So using sigma notation will be the summation from k is equal to 1 to 5 of the expression k plus 3. Part B, we got 6 plus 12 plus 18 plus 24 plus 30 plus 36. All right, so let me go ahead and write that down. For that, of course, we need the summation notation. I'm going to start with k equaling to 1, and let's count up how many numbers do I have here in this summation, in this sum. That's 6, so it would be from k equal 1 to 6. And let's look at these numbers here. These look like they're multiples of 6. So I know it's going to be a factor of 6 times, or what number times 1 will give you 6? It has to be 6, so it'll be 6k. And k is going to start off as 1, so that means 6 times 1 will give us a 6. 6 times 2 is 12. 6 times 3 is 18. 6 times 4 is 24. 6 times 5 would be 30. 6 times 6 would be 36. So the summation from k is equal to 1 to 6 of 6k. That would be the sum using sigma notation. Now part C, we got 1 to the 8th, plus 2 to the 8th, plus 3 to the 8th, plus 4 to the 8th. Well, that's simple. So the summation from k is equal to, we're going to start off with the 1, and there are 4 sums here, or 4 numbers that we're adding. So the summation from k is equal to 1 to 4. And the only number that's not changing is that exponent of 8. Here, these numbers are. So it's just got to be k to the power of 8. Because that's 1 to the 8th. Then for 2, you have 2 to the 8th. For 3, 3 to the 8th. And then for 4, 4 to the 8th. And then part D, 1/9 plus 1/10 plus 1/11 plus 1/12. I want to express that using sigma notation. So I have the summation from k is equal to, let's start off with the 1, and then we got 1, 2, 3, 4 terms, so our upper limit would be 4. And let's think about this for a moment. The 1 in the numerator is staying the same, so I know I got 1 over something. If I'm starting up with 1, 1 plus what number will give me 9? Has to be 8. So that denominator will have to be k plus 8. And it does make sense because if k is going to be 1, then 1 plus 8 would be 9. K is 2, 2 plus 9, 2 plus 8 would be 10. For 3 plus 8 is 11. And for 4, 4 plus 8 would be 12 in the denominator. Okay, so that's how we express the following sums using sigma notation in this case. Now on the next page, evaluate the following expressions, okay? Now in this case right here, instead of using the formulas that I gave you here, which I'm going to do on a second video, I'm going to use the graphing calculator to do this. I'm going to show you how to do this on the TI-84 Plus calculator. Okay, and it's got to be a TI-84 Plus calculator or better for you to do this. So like in part A, let's say I got the summation from k is equal to 1 to 20 of k. Okay, so here's what we do first on the graphing calculator, and I might need to zoom out a bit. All right, so what I'm going to do here is press the math key. I'm going to use my down arrow to come down to this menu item that says summation with the sigma notation. You can highlight that and then press enter. It will give you the sigma notation, and it will give you spaces to fill in. So here's what we're going to do here. And personally, I do not like to use any of the green letters that are up here on the calculator. Because even though it says K, that means you have to press the alpha key and then find K, which is, in this case, that left parentheses on the calculator. You know what I want to do? I'd rather use X. So I'm going to do this. Just press xt theta n for the x. And then it's equal to that lower limit, which is your 1. You'll type that in. And then use your up arrow key to go to the upper limit part. In this case, that's 20. You'll type in 20. And then use your right arrow key to go inside, put the cursor inside the box, inside the parentheses. And in this case here, this variable that you put here has to be the same. And in this case, they say k, but we're using x in this case. So I have to press xt theta n. Notice that these variables have to be the same in order for this to work. Then I'm going to use my right arrow to get out of the parentheses. And then finally press enter. That will give you the sum right there. So the summation from k equaling to from 1 to 20 of k would be 210. Summation from k is equal to 1 to 20. K equaling from 1 to 20 of k would be 210. All right, now let's try part B, which is 3k plus 1. And that's the summation from k equaling from 1 to 7. So again, we press the math key, down arrow to summation, gives you this. And I'm using x instead of the k that they have here. So I'm letting x equal 1 from 1 to 7, and let this be 3x plus 1. So I'm going to use xt theta for the x. And then after the equal sign, it takes me to that box. I'll type in 1, then use the up arrow key for my upper limit, that's 7. Use my right arrow key to enter this expression. So instead of 3k plus 1, I'm just going to do 3x plus 1. So it'll be 3 xt theta and then plus 1. And I'm going to use my right arrow key to get out of the parentheses. And then press enter. That will give you the answer of 91. So the summation for k equaling from 1 to 7 of 3k plus 1 is equal to 91. Or better yet, let me go ahead and put the answers down here. 210, then 91. Now part C is the summation for k equaling from 1 to 7 of k squared. Instead of k's, I'm going to use x's here, so let's do this. Press the math key. Use your down arrow key to get to summation. And I'm going to use xt theta n for the x. And then I'm starting at 1, so I'll type in 1 for x equals 1, and then up arrow up to 7. That's the upper limit. And then use my right arrow key to get out of it. For k squared, I'll say x squared, so I'll be getting the x, and then I'm going to square it. And notice that it always gives you the parentheses here. That's the nice thing about it. Hit enter, you'll get 140. And then part D, we got the summation for n is equal to 1 up to 7 of 3 plus n squared. And I'm going to use x again. So math, down arrow all the way down to summation. And I'm going to use x again, so it'll be xt theta n for the x. Our lower limit is 1, so we type in the 1. Upper limit, use your up arrow key, is 7 again. This time it'll be 3 plus n squared, but I'm going to use 3 plus x squared, since I'm using x in this case. 3 plus, get the x, and then square it. So it'll be 161. Okay. Part E. The summation from m is equal to 1 to 4 of 2m plus 2 divided by 5. All right, so to enter this in, let's do math, go down to summation, and I'm using xc theta n for the x, and that'll be from 1 up to 4. Now for that 2m plus 2 divided by 5, let's do this. Left parentheses, I want this all divided by 5, so that 2m plus, or 2x plus 2 will be in parentheses. So left parentheses, 2 xc theta n for the x plus 2, close parentheses, divided by 5. And then press enter. Okay, this says 5.6, but if I press the math key and then number 1 for fraction, it will be 28 over 5. Or 28 fifths. Okay, so if it gives you a decimal and they want it in the form of a fraction or a simplified fraction, press the math key and then select number 1 to change it to a fraction. All right, part F is the summation for j is equal from 1 to 5 of 2j minus 3. All right, math key. Go down to summation. We're going to use x instead of j this time, so it'll be x, and then this is from 1 to up arrow key 5. 2j minus 3 will be 2x minus 3, so it'll be 2, get the x, minus 3. Right arrow to get out of it, and then press enter. Should get 15. And then part G will be the summation for k is equal to from 1 to 8 of k times the quantity for k plus 9. So math, go down to summation. I'm going to use x instead of the k that they have here, so it'll be x is equal to 1 up to 8. Now for the k times for k plus 9, it'll be x times the quantity for x plus 9. So get the x, and then left parentheses, 4, get the x, plus 9, close parentheses. And hit enter. And you'll get 1,140 as the answer. And then finally for part H, the summation for n is equal from 0 to 4 of the sine of n times pi divided by 2. All right, for this one, you want to make sure that you're in the radian mode. So press the mode key. You want to make sure that radian is highlighted. If it's not, you want to use your down arrow key to put the cursor on top of radian and then hit enter. Okay, and then second quit to get out of it. Now, math, go down to summation, and I'm going to use x this time, still going to use x. X is equal to 0 up to 4. And then inside the parentheses, I'm going to press the button that says SIN for the sign. And then, let's see here, I'm using x, so I'll press xc theta for the x. And then for pi, I'm going to do second and hack for the pi, because right above the hack key is the pi. So it'll be second hack for pi divided by 2. And I'm going to close the parentheses. Then hit enter. In this case, I got a negative 1 times e to the negative 13th power. But if you were to write that out as a decimal value, it would be like a point, 12 zeros, and then the 1. But we can say 0. Because if you were to do this manually, now I'll show you here, if you did this manually like I did here, you'll have sine of 0 pi over 2 plus sine of 1 pi over 2 plus sine of 2 pi over 2 plus sine of 3 pi over 2 plus sine of 4 pi over 2. Well, 0 times pi is 0 divided by 2 is 0. 1 times pi over 2 will be sine of pi over 2. Sine of 2 pi over 2 will be sine of pi. Sine of 3 pi over 2 will still be sine of 3 pi over 2. And then sine of 4 pi over 2 simplifies to sine of 2 pi. And then you have to use your unit circle to know that sine of 0 is 0. Sine of pi halves is 1. Sine of pi is 0. Sine of 3 pi over 2 will be negative 1. And sine of 2 pi will be 0. Here, 1 and negative 1 ends up being 0, so that means the summation for n is equal to from 0 to 4 of sine of n pi over 2 will end up being 0 as the final answer. Okay? All right, so that's how we use the graphing calculator, the TI-84 plus calculator, to do summations. Because we're going to be using that when we're dealing with Riemann sums and sigma notation. So with sigma notation, a Riemann sum has the convenient compact form of this: f of x star sub 1 times delta x plus f of x star 2 delta x plus and so on up to f of x star sub n delta x. That's going to be this right here. The summation for k is equal to from 1 to n of f of x star sub k times delta x. That's the more compact form. And to express left, right, and midpoint Riemann sums in sigma notation, we have to identify the points x sub x star sub k. So in this case here, for left Riemann sums, the left endpoints of the subintervals are going to be this: x star sub k will be equal to a plus the quantity k minus 1 times delta x. That's for the left Riemann sum. And k is going to be from 1 up to n. Now for the right Riemann sum, your right endpoints of your subintervals will be this: x star sub k, which will be equal to a plus k times delta x. A plus k times delta x. And that's also for k going up from 1 up to n. And then for your midpoint Riemann sums, the midpoints of your subintervals are going to be this: x star sub k equaling to a plus the quantity k minus 1/2 delta x. That's going to be for k is equal to 1 up to n. Okay, so now that's how we use those. And we can compactly write our 3 Riemann sums as this. And here's the definition. Let's say f is defined on the closed interval AB, which is divided into n subintervals of equal length delta x. If x star sub k is a point on the k subinterval x sub k minus 1 to x sub k for k equaling to 1 all the way up to n, then the Riemann sum for f on the closed interval AB is this: the summation for k equaling from 1 to n of f of x star sub k delta x. And we have 3 cases. Your left Riemann sum is this: if x star sub k is equal to a plus the quantity k minus 1 times delta x. Your right Riemann sum will be this: if x star sub k is equal to a plus k times delta x. And then your midpoint Riemann sum would be this: if x star sub k is equal to a plus the quantity k minus 1/2 times delta x. Okay, and I do have one example that is related to this. So on the final page, complete the following steps for the given function f and the interval. So in part A is this: for the given value of n, use sigma notation to write the left, right, and midpoint Riemann sums. Then evaluate each sum using a calculator. Part B, based on the approximations found in Part A, estimate the area of the region bounded by the graph of f on the interval. And here we got the function f of x equal to the square root of x for the interval 0 to 5. And here our subintervals are going to be 40. So n is equal to 40. Now in the previous examples on the previous video, we did have n equaling to a small number. So we were able to do those, but now we got n equal 40 this time. So we're going to have to use the sigma notation. All right, so let's identify what we got here. Our closed interval is from 0 to 5, so a has to be 0, b is 5, and n is going to be 40. So let's find out what delta x is, that change in x. That's b minus a divided by n. Well, b is 5 minus a, which is 0, divided by 40. So 5 minus 0 will be 5, and I have 5 over 40. If I reduce 5 40ths, that's going to be 1/8. So the delta x, change in x, will be 1/8. So in part A, we're going to start off by finding our left Riemann sum. Okay, there's something else I need to find out. If I'm going to use a left Riemann sum, I need to find out what x star sub k is. And that left Riemann sum x star sub k will be a plus the quantity k minus 1 times delta x. So is a plus the quantity k minus 1 times delta x. Now let's substitute here. A is 0 in this case, plus, and then we got k minus 1 times delta x is 1/8. So that means all we'll have is just k minus 1 times 1/8. And this k minus 1, I'm going to put that over 1. So that means I'll have k minus 1 all divided by 8. So that would be x star sub k. X star sub k. Okay. So now we're going to use this sigma notation here. The summation for k is equal from 1 to n of f of x star sub k times delta x. And I'll go ahead and write that out. Summation from k is equal to 1 to n of f of x star sub k times delta x. And we're just going to do some substitution here in this case. We got the summation from k is equal to 1 to n, in this case is 40. So it'll be the summation for k is equal to from 1 to 40 of f of x star sub k, in this case, is the k minus 1 over 8, times delta x. Well, delta x was 1/8. Okay. So does everyone, well, if you have questions, do reach out to me by email. So I'm going to pull the 1/8 in front. That's a constant. I can use the constant multiple rule for that. And then multiply that by the summation of k equaling to 1 to 40 of, now, here's f of x. F of x is the square root of x. That means I can take this k minus 1 over 8, replace that, put that in place of x. So that means I have a square root of k minus 1 over 8. And this is all underneath the radical, by the way. Now I can use my graphing calculator to come up with this value here. Okay. And I like to use X when I do this in the calculator. So now let's press the math key, go down to summation. Here we go, summation. And instead of K, I'm going to use X in this case. So it'll be X equal to, starting with a 1, up arrow, 40. We'll type that in. Right arrow key. Now here we need to enter this right here. For the square root, let's do second X squared for the square root. And then for the K minus 1, I'm going to put that in parentheses. So left parentheses, instead of K, I'm using X. So it'll be X minus 1, close parentheses, divided by 8. Use my right arrow key to get out of the radical, and use the right arrow key again to get out of the parentheses. And whatever I get for this, I need to multiply that by 1/8. Okay, so I don't want to forget that. So if I press enter, it's this number, 58.4392575, but I need to multiply that by the 1/8. So multiply that by 1 divided by 8. It will be this number. Let's say to 3 decimal places, this will be approximately 7.305. Okay. I did this in the calculator. Whatever I get for that, I multiplied it by 1/8. Okay. So my left Riemann sum is approximately 7.305. So that's how I calculated the left Riemann sum. Now for the right Riemann sum. I also have to do that as well. That's going to be x star sub k, and that's equal to a plus, according to this, a plus k times delta x. So my a, of course, that's going to be that 0 up there, so it'll be 0 plus k times my delta x is 1/8. So if I simplify this a bit, this will be 1/8 times k. Okay, and I'm still going to be using that notation there, the summation for k is equal to 1, k equaling from 1 to n of f of x star sub k times delta x. And so if I substitute, that would be the summation for k is equal from 1 to n. Again, that's going to be 40. And this is f of this right here, the 1/8 k, times 1/8, which is delta x. My f of x, of course, is the square root of x. So in place of this x, I will put the 1/8 k in its place. So I'll still have the summation for k equaling from 1 to 40 of the square root of 1/8 k. And I'll pull that 1/8 out in front right here. So let me do that first. So I have 1/8 times the summation for k equaling from 1 to 40 of the square root of 1/8 k. Now we can use the graphing calculator. I'm going to do this first and then multiply it by 1/8. So press the math key, go down to summation, and I'm going to use x instead of the k this time. It's easier for me to do it that way. So it'll be x is equal to 1, up arrow to the upper limit of 40, and then right arrow to go inside the parentheses, For the square root of 1/8 k, you do second x squared for the square root. And then I would do, let's see, left parentheses 1 divided by 8, close parentheses, times x, since I'm using x here as my variable. Right arrow to get out of the square root, and the right arrow again to get out of the parentheses. So if I press enter, I'll get this value, but that's only for the summation. I got to do 1/8 of that, so I'll take that, multiply it by 1 divided by 8, or you could divide by 8 if you want to. You'll end up getting to 3 decimal places 7.584. So that represents the right Riemann sum, 7.584. And then for the midpoint Riemann sum, I have to do that as well. This will be x star sub k, and that's equal to 8 plus the quantity k minus 1/2 times delta x. That's this right here. 8 plus k minus 1/2, that quantity is multiplied by delta x. All right, so let's figure out what that's going to be. My a is 0 plus k plus the quantity k minus 1/2 times delta x, that was 1/8. So if I distribute the 1/8 over the k minus 1/2, this will be 1/8 k minus 1/8 times 1/2 will be 1/16. And let's do this here. I'm going to use equivalent fractions here. The common denominator for 8 and 16, that's 16. And I've already got the 16 where that 1 is, so I have minus 1. To make this one have a denominator of 16, I need to multiply the numerator and the denominator by 2, because 8 goes into 16 2 times. 2 times 1 will be 2, so it'll be 2k minus 1 all over 16. So I'm still going to be using this notation, the summation for k equaling from 1 to n of f of x star sub k times delta x. And this will be the summation for k is equal to 1 to n, which is 40, of, in this case, f of x star sub k. This time is at 2k minus 16. 2k minus 1 all over 16 times 1/8. That 1/8 is a constant. I'll pull that out in front. So it'll be 1/8 times the summation of k equaling from 1 to 40 of, and in this case here, my f of x is still going to be the square root of x, so I'll replace the x with that 2k minus 1 over 16. So this will be the square root of 2k minus 1 over 16. The whole thing is underneath the radical. Now here I can enter this in the calculator. So now press the math key, go down to summation, and then I'm going to use x, so it'll be x is equal to, x equals to from 1 and then up to 40. And then for the square root, second x squared for that. And I'm going to put 2k minus 1 in parentheses, so left parentheses, or 2x minus 1 in parentheses, I should say. So it would be 2xt theta n for the x minus 1, close parentheses, divided by 16. Use your right arrow key to get out of the radical and the right arrow key to get out of the parentheses. Whatever I get for this, it'll have to be multiplied by 1/8. So that's this right here. So I need to do that amount times 1/8. Can't leave that out. So the 3 decimal places, this will be approximately 7.456. That represents your midpoint Riemann sum. Your midpoint Riemann sum. Okay. So all of this represented part A, finding the left, the right, and the midpoint Riemann sum. Part B is, based on the approximations found in part A, estimate the area of the region bounded by the graph of f on the interval. Well, by looking at these values that we have here for the left, right, and midpoint Riemann sums, the best estimate of the region will come from our midpoint, because we found out from an example from another video that the left Riemann sum underestimates the area, and the right Riemann sum overestimates the area under the curve. The midpoint gives the best estimate of the region bounded by that function. So we're going to say here that the midpoint Riemann sum gives the best estimate of the region. That's bounded by f of x on this interval 0 to 5. So that means here the area will be approximately 7.456. So we'll use that as the area that gives the best estimate of the region bounded by the function f of x equaling to the square root of x and the interval 0, 5. Okay, so that wraps up this video, part 2 of this video for section 5.1, dealing with approximating areas under curves. Feel free to reach out to me if you have any questions about anything that's presented in this video or any of the homework problems that are in my math lab.